Hi, I'm going to talk about types of energy, conservation of energy, and power. So first, types of energy. You've already been introduced to one, so I'll just remind you of that one. One, kinetic energy. Kinetic energy is energy associated with motion of an object. So if I have an object moving with some velocity v, that object has some energy, and we say it has some kinetic energy that's given by 1/2 mv squared. And when you compute that, you get an energy in joules. So you've already seen that. 2, potential energy. There's more than one type of potential energy. There's several types. I'm going to talk about 2 types in particular. The first is gravitational potential energy. So suppose I have some object like a ball, and I lift it up through some height y above the earth. We say that that object has some potential energy. So I start with it here, and I lift it up through some height here. So even though it doesn't have any velocity, it still has energy. It has the potential to do work. If I were to release it, it could gain some energy, some kinetic energy, for example. So we say it has gravitational potential energy. How much potential energy, I'm not going to derive. It's derived by computing the work done by gravity, but that gravitational potential energy is just given by mgy. This is its weight, mg, times the distance over which you move it. So the more it weighs, or the further you move it, the more energy you give it. That makes perfectly good sense. That's gravitational potential energy. This is the energy associated with the position of an object above or below the surface of the earth. So we'll say this is energy associated with position of an object above the earth. And of course, if it's negative, it'd be below the surface of the earth, or it could be above or below something else. That's called the potential energy, gravitational potential energy. There's also another potential energy. This was potential energy of gravity. There's potential energy, there's elastic potential energy. And for that, I have to do a quick aside. So I'm going to do elastic potential energy in just a moment. But so an aside. I'm going to talk about springs. They're surprisingly important because there are many things in nature that behave like springs. For example, even bonds and molecules behave a lot like springs. But suppose I have a spring here with some mass on it. I could compress that spring, and that would give it energy. I could pull that spring, and that would give it energy. But I need some measure of the stiffness of the spring. So I find experimentally that how much I compress or pull this spring, that the force the spring applies, so suppose I pull this spring out through some distance, this is pulling it out, that the spring then applies some force that's proportional to how far I stretch it. So if I stretch the spring a little bit, the force the spring pulls back is a little force. If I stretch it a lot, the force is big. That makes good sense. If I compress the spring, then the spring pushes back with a little. If I compress it a little bit, the spring pushes with a little force. If I compress it a lot, the spring pushes with a big force. This is just called Hooke's law. It's actually not a law, even though it's called that. It's actually just an approximation. Springs approximately behave that way. And this K is called the spring constant and is a measure of the stiffness of the spring. So if the spring is really stiff, that K is really big. If the spring is really floppy and not very stiff, that spring is small. It has units of newtons per meter. So for example, if K is, 10,000 newtons per meter, that's a very, very stiff spring. And if that K is 5 newtons per meter, that's a very wimpy spring. So that K is just how stiff is the spring. Now you can imagine now, if I want to talk about energy stored in that spring, if I compress this spring, I've given it some energy. What kind of energy? Elastic potential energy. So potential energy, so that's the aside. Potential energy, elastic, or potential energy of a spring is given by, it turns out, 1/2 kx squared. We haven't derived that. Your book derives it. It's not obvious, by the way. You shouldn't look at that and say that's obvious. But it does capture, it does seem at least reasonable that the stiffer the spring is, the more potential energy you get when you compress it or stretch it. It turns out this potential energy depends on the square of how much you compress or stretch it. So this is elastic potential energy. So that's another type of potential energy. So again, the energy is stored in the spring. If I compress this spring, it has the potential to do work, and we call that a potential energy. Now so that was our second type of energy. We had kinetic energy was our first type, energy of motion. Potential energy was our second type, where we had energy stored, such as energy above the surface of the earth because of gravity, or energy in a spring system. There's a third type, and that's just thermal energy, or you might know it as heat energy. And this is the energy of random motion of molecules. Not just the random motions, but random motions of molecules colliding with each other. Colliding with one another. So when you rub your hands together and they get warm, it's the motion of the molecules colliding with each other that causes the warmth. So friction tends to cause, or does cause, thermal energy. It's not the only thing that causes thermal energy, but it can cause this. So that's another type of energy. So we've got kinetic energy, energy of motion, potential energy, energy of position, and thermal energy, heat energy. Those are our three types of energy. There are other types, but these are the ones that we need to deal with this semester. Now, and just as a review, our kinetic energy was given by 1/2 mv squared. Our potential energy of gravity was given by mgy. Our potential energy elastic, or of a spring, was given by 1/2 kx squared. And our energy thermal, we don't have an equation for. We have to get it some other way. There's no simple equation for that. We can sometimes get it by the difference in some of these other energies, and I'll show you that. So, why is this so important? It's actually of incredible fundamental importance because of topic 2 in today's lecture, the law of conservation of energy. This is one of the most fundamental laws in all of nature as far as we know. This law says energy cannot be created or destroyed, merely transformed from one type to another. You should memorize that. Energy cannot be created or destroyed, merely transformed from one type to another. So when I take this ball and I give it potential energy, it has a certain amount of potential energy. I can let go of the ball, and that potential energy went away, but it became kinetic energy as the ball sped up. So the potential energy didn't disappear from the universe, became kinetic energy. But you say, aha, I see a problem in what you're saying, because now the potential energy is gone and the kinetic energy is gone. It went into thermal energy. The ball in my hand are now a little warmer than they were before I dropped the ball. So the chemical energy of the 2 eggs I ate for breakfast this morning went into lifting the ball, gave gravitational potential energy. That potential energy became kinetic energy. The kinetic energy became thermal energy of the ball in my hand. So none of the energy got created, none of it got destroyed. It all just was moving around from one type to another. That's the law of conservation of energy. It's extremely powerful. It helps us in understanding many things. It helps us in calculations. So just in this idea of dropping the ball, if we have a ball of mass m at height y, and we want to know how fast is it going at the bottom of its path, v. Now we can calculate that using uniform acceleration equations, but it's remarkably easy with energy. We start with its initial energy, mgy, that's gravitational potential energy. Its final energy is kinetic energy, 1/2 mv squared, and provided that no energy was lost, and by lost I mean goes into thermal energy. You can't really lose it from the universe, but we sometimes call it lost if it goes into heat. So provided no energy went into heat, these are equal. Initial energy equals final energy. The m's cancel, and v is just the square root of 2gy. And we're done. Conservation of energy. So I'm going to do 2 examples of that, and then we'll talk about our last topic. 2 more elaborate examples of this law of conservation of energy. Again, one of the most important laws that you'll see all year in the class. So, example 1. Suppose I have a skier at the top of a ski slope, and she skis down the slope. Let's give her arms or something. This slope has height y equal 8 meters. She has a mass of 65 kilograms. And I want to find her speed at the bottom. I'm going to do 2 parts to this. The first part is so like the first example that you'll wonder why I'm doing it, but then I'm going to do the second part. So it turns out this conservation of energy for gravity doesn't depend on the distance this way. The gravitational potential energy just depends on height. So if I set the initial energy equal the final energy, and her initial energy was just mgy equals her final energy, 1/2 mv squared. That's assuming no energy went into heat, went into friction heating. And again, the m's cancel, and v is just the square root of 2gy, or 9.8 meters per second squared, 8 meters, square root, and that gives me 12.5 meters per second. Very straightforward. If she had a running start here, then the beginning energy would have been a 1/2 mv squared plus an mgy, where v would be the speed of a running start. Whatever her energy is at the top. If she had been launched with a spring, it would have been a 1/2 kx squared plus an mgy. You just take the initial energy and set it equal to final if no energy is lost. And again, lost means goes into thermal energy. Now, this is case 1 for this. Case 2. What if you discover at the bottom that she was only going 9 meters a second. That means some energy went some other place. It went into plowing the snow out of the way, went into moving the snow, it went into heat, it went into other places besides these. And so we can compute the energy lost to other forms by just saying it's the difference in these two energies. So the energy to other forms is just E final minus E initial. I hope that's obvious. It's just, if these are not equal, then the energy that went other places is just their difference. So E final would be 1/2 mv squared minus E initial would be mgy. So this would now be 1/2, 65 kilograms. I told you her mass. V squared, V is her real speed at the end, 9 meters per second, squared, minus 65 kilograms, 9.8 meters per second squared. The height is still 8 meters. So this gives me 2633 joules minus 5096 joules. So she started with 5096 joules of potential energy. When she got at the bottom, she only had 2633 joules of kinetic energy. That other energy had to go somewhere. It went into heating the skis, heating the snow, pushing the snow out of the way, went into other places. So the energy that went to other places was minus 2464 joules. Well, often in our assignments call this the work done by friction, and that's usually what it is. So there's an example. Let me do another example. So that was example 1. All right. Example 2. I wanted to do one with a spring. Suppose I have a spring and I compress it with a block on it from its uncompressed position would have been here. This would have been its x equals 0 position. That would be where the spring would be not compressed. And I compress it, put this block against it and compress it. I don't attach the block. I just push it against it and I'm going to release it and the spring is going to launch the block with some speed. This, I compress it by 5 centimeters. And this is a fairly stiff spring. This is 100 Newton per meter spring. It takes 100 newtons to compress it every meter. And I just want to know how fast this block would be going if I launch it with this spring. I have to know the mass of the block, and so I use a 500 gram block, so a half kilogram. I just take the initial energy. Now the initial energy is elastic energy, 1/2 kx squared. Set it equal to the final energy, 1/2 mv squared, and solve for what I don't know, in this case v. The halves cancel. V is then the square root of k over m times x. Notice the x is not in the square root because it's squared and you take the square root. So V is 100 newtons per meter over 500 grams is a half a kilogram. You have to do this in kilograms. Square root. X is 0.05 meters. Notice I didn't put the minus in because I know it's going to the right, and I squared this and then took a square root. So I have to use my own logic to decide if it's plus or minus. And this gives me 0.71 meters per second. But again, the logic is set the initial energy equal to the final energy, provided you know no energy got lost to work done by friction or other forms. If energy you know did get lost, then you have to take the difference between the final energy and the initial energy. All right, last topic of the day, power. Power. Power is the rate at which work is done or energy is transferred. There are 2 R's in transferred, I don't know. Rate at which work is done or energy transferred. I think there might be 2 R's there. Anyway, so power is either work over time or energy transfer over time. This just says it's the energy over the time. So its unit is a unit of energy over unit of time, a joule per second. By definition, that is a watt, the symbol W. So when you buy a 100-watt light bulb, it means 100 joules of electrical energy every second are being transferred into light and heat. So it's just the rate at which energy is being transformed from one type to another. For a light bulb, it's electrical energy to light and heat. So the example we just did for a spring, we compressed a spring, we had a block on it, we launched that block, we turned the potential energy of the spring into kinetic energy, and so the power in this case would be delta E over delta T. In this case, we started with 1/2 kx squared, and it turned into 1/2 mv squared. So our delta E is either this or this in this case. Sometimes I see students take the difference in these two. There might be occasions when you do that if you want to know the energy that turned into heat. But what we want to know in this case, what I'm asking in this question, I want to know the power in turning this energy into that energy. So this delta E is either this or this. So I'm saying this delta E is 1/2 kx squared. That's 1/2. The K was 100 newtons per meter in that example. X was 0.05 meters in that example. So this energy that was being turned into from potential to kinetic energy was 0.125 joules. I didn't give you a time in the example, so now I will. Springs release energy really quickly, so I just guessed that the time was maybe 100 microseconds that it takes for a spring to go bang, because that's really quick. So this would be 0.125 joules over 100 times 10 to the minus 6 seconds, and that is 1250 watts or 1.25 kilowatts. So to get power, you just divide the energy transferred by the time, whatever that energy transfer happens to be. Well, that's a lot. You'll have a lot to think about and to practice in your homework and in class. So see you soon. Bye.